So this is the diagram, right? You have the basic cube and 1 1 1. On the x it cuts at 1, on the y it cuts at 1, on the z it cuts at 1. So in drawing, this is the simplest type of plane. And the atoms that it is intersecting, of course it is intersecting these corner atoms, and it is intersecting some atoms on the faces. It is intersecting face atom, face atom, face atom, and so on. So you will have to find out the number of atoms which are there. Then this base diagonal is root 2a. Of course you understand that. And based on that, this diagonal and so on will be different, right? So if you want to find area of a triangle, then right, the height of the triangle is this, and you will see by simple geometry this comes out to be root 3 by 2a, right, and so on. So right, so this is the diagram. From here you find the equivalent number of atoms cut by this plane and the area. So the area, of course, if it is a triangle, it is half base into height. So half is there, base is root 2a, height is root 3 by 2a, and therefore you can find the area. So let us proceed and see. So here we are trying to explain. You read it, and by reading it you will find out that the total number of atoms are 2 equivalent anions here, and the rest is the same. A is equal to 2r plus r, and let us proceed further. I will show you. I am showing you here the diagram, and I am telling you that the area is half base into height. The base is root 2a. The height is root 2a by 2 whole square plus root 2a whole square, and so on. So it is root 3 by 2a. You can do it yourself. So half into root 2a into root 3 by 2a. So this is the area. And because you have found the a was equal to 2r plus 2r, so you have already found it. So the area of this plane is this much. And there are 2 ions on this one. Therefore, 2 divided by this number is 10.2 oxygen ions per nanometer square. And once again, because calcium oxide, whatever is true for oxygen will be true for calcium. So if the planar density of oxygen is this, then the planar density of calcium is also the same, right? So this is there. Of course, we can draw the geometry for the other one also. We were assuming that the corner ones are oxide, so the center ones are oxygen. Then we can shift them. Because each one of this is surrounded by the other. So now we can say the corner ones are calcium and the center ones are chlorine, and therefore this is the same. Okay. So with this, we are here. Let us take a very quick break. Welcome back after the short break. You see, we have done 2 classes of crystal structures for ceramic, the cesium chloride family of ceramics and the sodium chloride family of ceramics. Now this is the third popular family. This is zinc sulfide, but commercially it is called zinc blende, right? So zinc blende or zinc sulfide is the third family of crystal structures for ceramics. And all the types of crystal problems that we can try to do, we have already done, right? Atomic packing factor, density, linear density, planar density. So we have done all those type of examples. So we can do that for any type of crystal now. The only thing will be that because it is a ceramic crystal, so compared to a plain metal crystal, in a plain metal, all atoms are sodium or all atoms are iron. But this here, one is sodium, one is chlorine, 2 types, right? One is cesium, one is chloride. So that difference is there. So now this is the third type. But if you see, I have left it as a self-study for you because we have covered everything that we need to cover in ceramics and so on with the examples of sodium chloride type and cesium chloride type. So here I'll very quickly show you the slides, but please read it yourself. And if there is any problem or anything like that, then you can do that. So zinc blende, right? This is the structure. right? This is the structure. It is still an FCC type. It is an FCC. If you see the light one, this one, this one, this one, this one, and on the face. So if this is, here they are saying it is sulfur, right? This is zinc sulfide. So this light one is sulfur. So all the four corners and in the face. If you take the right face, all the four corners and the center. So this is like this. But the atoms in the middle, the other atoms, the zinc atoms, are not like every interstitial site. They are only on special places. They are only on special places. So once you do the calculation and so on, you see that this is an FCC type. It is an FCC type. The structure is tetrahedral. The coordination number is 8. And cadmium sulfide, indium, I don't remember, AS, and all of these are also ceramics, which are the same as zinc sulfide in structure. You'll have to go back, and AS is arsenic, I think, SP I forgot, SE I forgot, selenium maybe, right? So all of these, and if it is sulfide, then it is a metal and a non-metal. But if it is zinc and selenium, then both of them are metal-metal. So some of them are metal, non-metal compounds, and some of them are metal-metal compounds in the zinc blend or zinc sulfide category. And immediately a problem that calculate the density, right? Calculate the density of zinc sulfide, and the ionic radius of zinc and sulfur are given. And this will be an FCC type and so on. So I will just show you. You can do it in detail later on yourself. So this is the diagram. This is the diagram. And if you look at this diagram, then we will say that, right, because it is like this, that is in the middle. Originally it is FCC. But the other one, if these are sulfides, then the zinc is in the middle of the, like a BCC. Zinc is the middle. So the middle one, if you remember, if you draw this diagonal, it is root 2a. But if you draw this diagonal, it is root 3a. So this root 3a is equal to radius of zinc and so on. And therefore, you have this relationship that root 3 by 4a is R of zinc plus R of sulfide. So, right? So this relationship is the only important thing. Once that is there, then of course the volume of the whole cube is a cubed, and here it is the radius of zinc, radius of sulfur, and so you find it. And once you have that, and density is the mass. And of course, if it is FCC type, then there are 4 of one kind, right? All the 4 corner atoms on a face and the center atom. So there are 4 equivalent atoms of one material. Therefore, there have to be 4 equivalent atoms of the other material. So 4 zinc into the mass of zinc, 4 sulfur into the mass of sulfur, Avogadro's number. So therefore, this is the total mass of the unit cell. And therefore, right, find a cubed and divide the mass upon this, and you will have the density. So right, so mass upon density, you will have it, right? So of course, finding the mass and density is okay. If it is FCC type, BCC type, you know the number of equivalent atoms. So the mass of how many atoms, volume is always a cubed. But if it is FCC, then what is a? If it is different, then what is a, and so on, right? So this is the third type. And in this chapter, there can be many more things. But for us at our level, we will do only these 3 types of crystal structures. The cesium chloride family of ceramics, the sodium chloride family of ceramics, and the zinc blend or the zinc sulfide family of ceramics. And with these, we can do any problems like density, linear density, planar density, and atomic packing factor, right? So this is it. And the next slide will be interesting.